Picking up where we left off. Just a couple more things about what we were just talking about. Here's the nucleus. Protons, positive charge, the total number determines the element. Neutrons, no charge, and the number in there determines the overall weight, so it determines the isotope. We will talk about the electrons eventually. Here's something we're going to get to very quickly. Periodic table. They're not always set up exactly the same way in terms of what's in the boxes is usually pretty normal, but where in the box they put the numbers varies. The one that I usually hand out in class has numbers in a slightly different place. But, and we'll talk about why it's constructed this way in a couple of minutes. But these little numbers up at the top, 1, 2, 3, 4, 5, 6, 7, 8, those are the atomic numbers. So that represents the number of protons in the nucleus. These numbers on the bottom represent the atomic mass. Now I mentioned we don't count the electrons to the weight. We just add the protons and the neutrons. So why aren't these whole numbers? A lot of you know the reason already. Is because this is a factor. What they do is that they look for any given element. There are a couple of different isotopes you could find that element in out in the real world. Isotopes that are unstable, not going to find as much of them. Isotopes that are stable, you're going to find way more of them. And that's how they get these numbers. They factor in the weight of the most common isotope plus the proportion of the most common isotope, the weight of the second common plus the proportion, the weight of the third plus the proportion, and that gives them these numbers. Now, for the smaller atoms, these numbers tend to be very close to a full number. 10.8, 12.0, 14.0, 16.00, 19.0. There's not a lot of different oxygen and fluorine isotopes. No. Is it 0.003 that had to go out 3 spots just to get a number here? The most common weight is going to be whatever that number rounds off to. Is it simple enough? When you get into the larger ones, the numbers get farther off, like for copper, 63.55. That's a good indication that there's a couple of pretty stable isotopes of copper that, and there may be a bunch of them, and it may not even round off to 64 for the most common one. So when you get up into this area, which we're not going to really talk about much, because biological materials mostly tend to be before you hit the bridge. But if I ask you a question about the most common isotope, and I give you a periodic table to look at, is that round the number off, and that'll tell you the weight of the most common isotope. Not much of a table. I forget if we just celebrated like a centennial birthday for the guy that kind of solidified this approach. Mendeleev, a Russian. Interesting backstory. If you know anything about Russia on the map, Russia is very wide. Is that Europe's over here, and then you go all the way over to the Pacific Ocean, and way over here and up north is Siberia. Not a very pleasant place. It's Alaska without the wacky politics. And I mean, they used to send people there to get rid of them. It's that nasty a place. But people live there. Right, is that there's populations that live there, and Mendeleev's family lived in Siberia. He was a fairly large family. I forget how many siblings he had. And early in his life, not super early, but I forget what age he was. I forget details a lot. His father died. His father was the support of the family. His mother was now scraping by to support the kids that she had. And Andreev, I think, was Mendeleev's first name, but he was, no question, super smart. And she knew that he had the most potential for success of any of the kids. And so she decided, I guess she went to line the other kids up and went, you guys are on your own. I'm taking him, and we're going someplace where he can actually meet his potential. And she got on a train and went, I don't know how many days it took, thousands and thousands and thousands of miles to Moscow, and introduced her son to people in their version of the Science Institute, and didn't live much beyond that. Kind of dumped him and says, he's a genius, foster this. And he became a scientist, kind of a foster scientist. Now, people had been looking for patterns in the chemistry of different elements, and they found that certain elements tended to act the same way chemically. And he thought that there was a way to organize the patterns that would tell you information. And he put together the first recognizable version, sort of. Whenever I tell you a story, these people this never comes out, whole cloth. It's always built on the work of others. But people get the credit. And he gets the credit for the periodic table. Now, because of the fact that he organized the table so that weights went up, I don't know that they had atomic numbers yet. I don't know that they knew about protons, but these things do get heavier as they go up. And then he organized them in columns according to how they react. He actually put together a table where there were blank boxes. And he was able to say, you see this blank box? There's an element that belongs there. We may not know of it yet, or we may not have done the chemistry on it yet, but we will find that there's an element here, that every box that I've set up on this table will have a corresponding element. We just have to find it. Or in later years, we have to make it. So this was a really important thing, the periodic table. We know stuff about the periodic table now that he didn't know. And that brings us to the last bit of an atom, electrons. I'll write this down eventually. Electrons are teeny tiny particles, right? For a very long time, they didn't even know if they had any kind of mass. They have a negative charge, though, and they crowd in around the positively charged nucleus, moving very, very, very fast, essentially everywhere at once at a certain distance out. When they first started to figure out what this was, you're always trying to, find comparisons from the real world, and so they decided that the electrons going around the nucleus was like planets going around the sun. They went, okay, they're in orbits. And before long, they found out, unlike the solar system where you have one planet per orbit, there were multiple electrons per orbit. So they went to orbitals. And then they realized they're not going in a circular plane like the planets do around the sun. They're just at a certain distance going everywhere. And so they're much more likely to be called shells now. But there are discrete levels that will only hold so many electrons before you have to start filling in the next level out. So, electrons. Whenever I put up something in quotes, it doesn't mean I'm quoting somebody. It means sort of. Is that Is he mature? Yeah, he's mature. Is that there's always the implication of it's sort of true, it's sort of not so true, or you're being sarcastic about it. So I mentioned they have a tiny, tiny, tiny bit of mass, but as far as anybody really works it, they kind of ignore that. So it's considered to have no mass. In an uncharged atom, the electron number equals the proton number. I slowed down there because I'm used to abbreviating numbers with a hashtag, but now people just see that as a hashtag and they find it confusing. So I wrote number out. These uncharged atoms are often called radicals, which gives you a clue as to stuff about them. A lot of radicals are very, very chemically reactive. We'll talk about why in just a minute. The most common radical released from biological chemistry is the oxygen radical. EG, which is an example, individual oxygen atoms will pop out of certain chemical reactions, and they have an equal number of electrons and protons, but for reasons we'll talk about in a minute, they are not stable. They're not chemically stable. There's a difference between nuclear stability and chemical stability. And so they will react with virtually anything they bump into, which makes them potentially dangerous. They can mess up your, the big molecules that they mess up your DNA and your proteins and your cell membranes and all sorts of things. So when people discovered that this type of chemistry worked in living things, they also very quickly found out that living things produce other chemicals that will quickly scarf up the radicals before they can do too much damage. And they called those chemicals antioxidants. A lot of those are very small molecules, type of molecule called coenzymes. We'll talk about those later. And they are called antioxidants, trying to control the damage potentially from oxygen radicals. And of course, like anytime we discover something that's protective in biological systems, we figure, well, if it's protective, then let's pump it up. And so people started to take a lot of antioxidant vitamins. They still do, right? Is that you know the term, you've heard antioxidants. And in certain circumstances, they can be very, very useful. They can be, healthful. But of course, when you look deeper at things, there's never a simple system at work. And they've discovered in the last 20 years that if we have chemistry that releases oxygen radicals, there are times when we put that to work. We use it to do good things. Some of your immune system cells, faced with an invader that they want to make fall apart, will pump oxygen radicals at them. Well, antioxidants kind of get in the way of that. So taking a lot of antioxidants can actually tamp down certain immune responses. Sometimes people with cancer, folks tell them, oh, you gotta eat healthy, you gotta eat lots and lots of antioxidants. They found out that a lot of our defenses against cancer involved this radical exposure to cancer cells, and antioxidants get in the way of that. So you're actually helping the cancer. Not all of them, but some of them, by filling your system with antioxidants. Another system that I'm aware of is that you want to build muscle. Well, how does your muscle know to increase the size of the cells? Because you don't tend to add cells, you tend to make them bigger. Well, part of the chemistry of muscle contraction releases oxygen radicals. And if you release a whole bunch of them, the muscle cells take that as a message to increase in size, to build up size. So if you're taking a lot of antioxidants, you don't build muscle as quickly. That's actually been confirmed with some pretty interesting experiments where they had people pumping iron, some of them taking a lot of antioxidant vitamins, some of them not, and then measuring the rate of muscle growth. And it turns out the muscles don't grow as fast with people taking lots of antioxidants. So some things are good things. There's always the possibility of too much of a good thing. And I will come back to this, and you have to remember later, oh, okay, this is why radicals are bad. So these things are zipping around the atom. In close to the nucleus is a smaller circle. So you can only fit a very limited number of electrons in close to the nucleus. You can only get 2 of them in there. The next level out is bigger. You can get 8 in there. The next level out, you can get 8 in, and then the shells start to do bizarre things that produces the bridge on the periodic table. And you get suborbitals, and it gets very complicated. And this is not a chemistry class, and so we're gonna basically, as I said before, we're gonna kind of ignore that. Is that we're just interested in the early capacity, because that gives me a way to explain what's going on. Oops. A shell that is chemically stable almost certainly has a full outer shell. You keep adding electrons in the outer shells. And if you got a shell that should hold 8 and you only got 7, oh no, that's potassium. Things reverse on the screen sometimes. Is that if you've got a shell that can hold 8, but there's only 1 in there, that is not particularly stable. If you have a shell that can hold 8 and you've got 7, that is not particularly stable. In fact, if you have any number other than the full number, and when you get into the suborbitals, it gets weirder. That is an atom that will react with things, sometimes very simply and sometimes not so simply. Periodic table has just 2 elements in the top line. Represents an element with 1 outer electron and an element with 2 outer electrons. An element with 1 proton, an element with 2 protons. Hydrogen and helium. When you get to the next level down, you've got 1, 2, 3, 4, 5, 6, 7, 8. 1 electron on the outside, 2, 3, 4, 5, 6, 7, 8. The next level, you get 8 again, and then it starts to get weirder. But that's what the columns represent. They represent how many electrons in an uncharged version of that atom, how many electrons are in the outer shell. So the columns are numbered. Column 1, 1 electron in the outer shell. 2, 3, 4, 5, 6, 7, 8. When you get here, it starts to go 1, 2, 3, 4, but the chemistry winds up getting more bizarre. There's actually 10 of them on the bridge because of that. So we're mostly concerned with these top 2. So what happens if you only have 1 electron in your outer shell? That's certainly not stable. Well, what's the easiest way to make it stable? That is, let's get rid of it. If we dump off that lone electron from the outer shell, now our outer shell is what used to be underneath it, but it's full. You used to have a balance between the positive charges and the negative charges. Now you've got a proton that no longer has a balancing electron if you're in column 1. So you have 1 extra positive charge. You now have a charged atom that's an ion. An ion can be a charged atom or a charged molecule. We'll get to molecules eventually. If you've got column 2, you only got 2 electrons out there. Dump them off, swap them with something that needs them, and exist in a much more stable form. Is a column 1, radicals are extremely reactive. Is you can get sodium, metal, little gray lumps, and you can make water explode with it. Just drop a little drop of sodium metal in. And the reaction of getting rid of those electrons as quickly as possible will actually destabilize the water and heat it up, and will ignite the hydrogen gas, and kaboom. On the other end, so column 1 and column 2 in nature tend to exist in the world in their stable form, which are positive ions. So sodium in regular table salt is a positive ion and not a little piece of silvery metal that'll make water explode. Magnesium is a positive ion, calcium, potassium, and so on down here. Years ago, when nuclear tests in the open air would release a radioactive version of strontium, one of the things that made people agree, let's stop doing this, let's stop testing these things, is the strontium would settle on grass, get picked up by cows, and wind up substituting for the calcium in some of the milk, but it was radioactive. So it was, doing nasty things to kids. Over here, here's column 8. Those all are very stable. Is that they used to call them in the inert elements, they still do to some extent. They don't react chemically with stuff. You can get them to do things with electricity, like neon, but they're not chemically reactive because their shells are full. Here's column 7, fluorine, chlorine, like in bleach. Chlorine in bleach is a radical. Chloride in salt is a pretty different sort of critter. Bromine, iodine. Now we get into the middle. Columns 3, 4, 5, and 6. Not that easy to steal 2. Not that easy to dump off 3. So those atoms are much more likely to go up to other atoms with shells that are not full and go, I'll give you one of mine if you give me one of yours. In some cases, I'll give you 2 of mine if you give me 2 of yours. That's what they call covalent bonding, and we'll pick that up in the next chapter. But the molecules, oxygen, carbon, nitrogen, tend to be integrated into molecules where the electrons are shared between the atoms. Not always equally, but that's the way it works. Okay, I have one more thing to cover for this chapter. I don't want to squeeze it into this already too long video. We'll have a short video to wrap up the chapter.